Hello everyone, it is the time of the year again. The IMO 2022 was held in Oslo, Norway from the 11th to 12th of July. This year's IMO features some really short and cute problems. So without further ado, let us take a look at the problems from day 1. There will also be a discussion of the statistics at the end of the video. So for problem 1, we have the following. Marianne has n aluminium coins which we denote by A and n bronze coins which we denote by B, arranged in a row in some arbitrary initial order. So over here we have n equals 4 as an illustration. A chain is any subsequence of consecutive coins of the same type. So for example, the BBB is considered a chain. Given a fixed positive k less than or equal to 2n, Marianne repeatedly performs the following operation. She identifies the longest chain containing the kth coin from the left. So for example, if k equals 5 for purposes of illustration, then the fifth coin from the left is this B, and the longest chain containing it is this BBB over here. And what she does is she moves all coins in that chain to the left end of the row. So for example, after moving it to the left end of the row, we end up over here with BBB, AAA, BA. And she repeatedly performs this operation. So next up, AAA will move to the left end of the row. And then what's the fifth coin is this B. So this BBBB now goes to the left end of the row. So, and now we end up with this, and so on and so forth. So we are supposed to find all pairs nk with 1 less than equal to k less than equal to 2n, such that for any initial ordering, at some moment during the process, the leftmost n coins will all be of the same type. So for this particular n and k and happen for this particular initial ordering, we do end up with all the 4 coins on the left at some point being the same type. So we are supposed to find all such pairs of k and n such that regardless of the initial ordering, we end up with this situation at some point in time. Okay, so this problem is actually not very difficult once you get some intuition about what is happening. So this is the basic intuition. If you have a chain over here, there's something on the left and there's something on the right, then moving the chain to the left will cause you to combine the 2 adjacent blocks into one single block. Now, this turns out to be the key to solving the problem. Essentially, what happens is when you move something to the left and it's not at the end, it's not a leftmost block or rightmost block, you end up inevitably combining the blocks to its left and to its right. So the number of blocks goes down. Now, does this always happen for k or for all pairs k and n and all configurations? Not really. Let us see where k and n might fail. So if k is less than n, actually quite clearly it can fail, because consider a configuration where you have n-1 copies of coin A and then n copies of B and then lastly the last copy of A. Now if k less than n, then obviously the k will be pointing at this A block over here, and it will just keep getting stuck. The A block will stay where it is and then nothing happens. So we will not be able to succeed. And you can see the problem here is because you pointed to the leftmost block and it keeps pointing to the leftmost block. This gives you some intuition later on to prove why other pairs of k and n works. Now similarly, if k is bigger than the ceiling of 3n over 2, it can fail because you will keep pointing to the rightmost block and nothing really gets achieved. Now this ceiling might be a bit hard to digest, so let us take a look. For example, when n is an even number, what is the construction? So just using n equals 4 as an illustration, k bigger than ceiling 3n over 2 essentially means k equals 7 or k equals 8. And you can tell what happens here. You're pointing to the rightmost block, this gets shifted all the way to the left, but now the new rightmost block is AA and you're pointing to it and AA gets shifted to the left. And no matter what you're doing, you keep pointing to the rightmost block and it just keeps shifting without actually combining any other blocks together. So this will also fail. And of course, if n is an odd number, then you have, let's say n equals 3 as an example, then you have one block that is slightly bigger than the other block of A, one block B that's slightly bigger than the other block of B. But if you put k large enough, and in this case, if you put k equals to 6, you'll always be pointing to the rightmost block. And then you shift this, but you still point to the rightmost block after that, and you shift this. and so on and so forth, you can never succeed. So I'll leave it as an example to write the block configuration for general n, but this idea should be quite clear. Now, what we will prove now is that for the other values of k, namely for k between n and ceiling of 3n over 2 inclusive, this will actually be able for you to succeed regardless of the initial ordering. To do this, we will actually, to do this properly, we will actually induct on the number of blocks. So by blocks, I mean like a whole chain of A, and then if it switches after that to B, then the next whole chain of B is considered a block, and so on. So obviously, if you have only 2 blocks currently, you are already in the desired end state configuration. So you're done. Now, if you currently have 3 blocks, then necessarily the first block is at most length n-1, right? So your k will definitely be pointing either at the third block, the second block, or the third block, and you can very easily check that once you move the second block over or you move the third block over, you'll end up combining and getting the final desired configuration. So there's nothing much to discuss here. So let us focus on the case where you have at least 4 blocks. And let's suppose that, let's say the number of blocks is B, and then you've proven for like the case B-1 and below, right? So here's a pictorial representation. K is somewhere from n to ceiling 3n over 2, and the intuition is that really you don't really keep pointing at the leftmost block or rightmost block for such values of k. Let's see the specifics. So firstly, here are some observations. If you are currently picking the innermost block, not innermost, but if you are picking an inner block, that means not the leftmost or the rightmost block, then after you shift it all the way to the left, the neighboring left and the neighboring right block will be combined, so the number of blocks will drop. If you pick the leftmost block, well, this is actually not possible because the leftmost block will have length at most n-1. So k being bigger than or equal to n will never point to the leftmost block. But it is possible that k actually points to the rightmost block. And in this case, the number of blocks stay constant because the number of blocks could stay constant, because you move the rightmost block all the way to the leftmost, and it is no guarantee that there's some block that combine, right? But the issue here is, can you always be picking the rightmost block? No, sometimes you pick the rightmost block, but actually other times you will end up with an inner block, and once the block count decreases, you are done by induction. So you need to prove that you are never in a situation where you end up always picking the rightmost block. So the answer is no. Can you always be picking the rightmost block? No, because a rightmost block that is picked must have length bigger than n over 2, right? Because k is from here to here. If k is like, let's say here, right? And you end up, this means picking the rightmost block. Your rightmost block must stretches therefore all the way to where k is. And this means that for k less than or equal to ceiling 3n over 2, you can very easily check for n or n even if you wish, that it means the rightmost block that is picked must have length bigger than n over 2. And so if you always end up picking a rightmost block, right, and you have at least 4 blocks, it means that after you pick this rightmost block, the new rightmost block also has length bigger than n over 2, and so on and so forth. So cycling through the at least 4 blocks of length bigger than n over 2 now gives the total row length to be bigger than 2n, which is a contradiction. So there you have it. This is the end of problem 1. Actually quite an intuitive problem where the key observation is that moving an inner block will cause its neighbors to combine. And then it's just a matter of working through when you pick the leftmost block, when you pick the rightmost block, and so on. Okay, so let us take a look at the next problem, problem number 2. So this is actually a really cute and short problem. You will see what the solution is like. So let us find all functions f from positive real to positive real such that for each x there is a positive real, there is exactly one y positive real satisfying this inequality. xfy plus yfx less than or equal to 2. So looks very strange and a very cumbersome sounding statement. So let's unpack a little bit. So what the question is saying is that for each x, there is a unique y that satisfies this inequality. So what we can do is we can call that unique y to be the partner of x. Now, one thing to observe is that if the partner of x is y, then actually the partner of y will be x, because you put you have x and then that partner y here, but now pretend you start with y first. And then of course, because this inequality already holds for the value x, then the x must become that partner. So it's a bit of a mind twisting, but hopefully you are able to comprehend and make this observation. So the next natural question to ask then is, could it be the case that actually everyone is its own partner? So far we say if the partner of x is y, right? But the partner could be itself. Y could be x. Could it be the case that actually everyone is its own partner? It sounds like a very lame thing, right? But it turns out, let's see what happens if they are A not equal B, such that they are partners. So partner of A is B and partner of B is A, and they are not equal. Now, by definition of partners, it means that this inequality is true. But by the definition that A is not a partner of itself, we also have this AFA plus AFA is bigger than 2. And of course, this is just AFA bigger than 1, and which is the same as FA bigger than 1 over A. Similarly, B is not a partner of itself. So this inequality must hold. Again, BFB bigger than 1 and FB bigger than 1 over B. So if we put these inequalities back to the original one, we get AFB plus BFA. Now FB is bigger than 1 over B, so you have this. And FA is bigger than 1 over A, so you have this. So you have this left-hand side bigger than this thing, which you can very easily check is greater than or equal to 2, let's say using AMGM, or the multitude of other ways that are possible. And this is a contradiction from this statement here, because this thing is strictly bigger than 2, but here is less than or equal to 2. So it turns out actually, everyone is its own partner. And this is a very powerful statement. Now you know that actually, xfx is less than or equal to 1 for all x. Wouldn't you wish that xfx equals to 1 for all x? Then you will be done because you have solved for fx. So let us assume on the contrary that there is some a that satisfies AFA strictly less than 1. And then we see what problems we get from here. Now intuitively, this will give some gap, and hopefully you can find multiple partners for A, which will be a contradiction. And indeed, the way we proceed is, let's say AFA is equals to 1 minus delta, where delta bigger than 0. This will help us give a concrete name to the gap that we are interested in. Now, of course, the intuition is that maybe you fudge A a little bit, and it ends up still being a partner because of this gap. So let's consider A plus epsilon, where epsilon is bigger than 0. And what I will show is that I can make this A plus epsilon into a partner of A if epsilon is small enough. And of course, this gives a contradiction because A is already a partner of A, but then A plus epsilon is another partner of A, which is contradicting to the question. Okay, so let us examine what is AF, A plus epsilon, and A plus epsilon, FA. Now, from the statement that we have already proven here, where fx is less than or equal to 1 over x, this tells us that AFA plus epsilon is less than or equal to A over A plus epsilon. And of course, here I just distribute out the sum. Now, A over A plus epsilon is less than 1. And AFA we've shown is 1 minus delta. So, for epsilon FA, if we can choose epsilon small enough, such that epsilon FA less than delta. Of course, this can be done because FA is some number, delta is some number. So we just make epsilon super small until this inequality holds. Once we do this, this thing will be less than delta. This is 1 minus delta. This is less than 1. The whole thing is less than or equal to 2. And so, indeed, we have shown that A plus epsilon is a partner of A. And as I explained earlier, this gives a contradiction to the problem statement. So it turns out that fx will be equal to 1 over x for all x. And lastly, this is the only candidate. We just very quickly check that this works, because for each x, the inequality is basically this, and this can only be satisfied for y equals to x. So what do you think of problem 2? It's actually a cute little problem. Each step I think follows quite naturally from a previous step, so it's not surprising that when you look at the statistics at the end of this video, actually the solve rate for problem 2 is higher than the average IMOs. So, but before we talk about statistics, let us take a look at problem 3, which is of course the hardest problem of day 1. Now, problem 3 is a number theory problem. We let k be a positive integer and let s be a finite set of odd prime numbers. Prove that there is at most one way up to rotation reflection to place the elements of S around a circle such that the product of any two neighbors is of the form x squared plus x plus k for some integer x. Now, in the original question, it's actually worded for some positive integer x. And of course, if I can prove the statement for some integer x, this is a stronger statement. So, in that sense, I have proven the original IMO problem. Now, there was actually a controversy on AOPS problem. You can read about it by looking up this problem. The positive integer x drew some unhappiness because in proving this problem, either you need to assume non-negative integer or in general a general integer. I don't think anyone came up with a proof where you directly prove the problem for some positive integer x. So this is just a sidetrack of the modification I make to the problem, but it's a more general problem to solve. Okay, so the way we approve this problem, actually the steps are again quite natural. Once you come up with the idea to induct on the size of S, and this is quite a common technique. So let us induct on the size of S, and we can see that for S less than or equal to 3, of course, there's at most one way to put the 3 numbers or less around a circle. So we don't even need to care about this condition. So mod S less than or equal to 3 is trivial. And the natural idea to use induction is, let's think about the largest prime inside S. And maybe you can remove it and reduce it to a smaller case. So to do this, we'll prove the following claim. If there are only at most two primes, or rather the claim is that there are only at most two primes Q and R less than P that can become neighbors of P. Moreover, QR is of that form x squared plus x plus k. Why does this solve the problem? Well, let's think about any valid configuration. For any valid configuration, by the first statement, it must be the case that we have Q and R as the neighbors of P. And of course, if Q and R are not even in S, then forget about it. Like you're just doomed from the beginning. There's no way to put the elements around a circle. But if Q and R are in P, or like a whole bunch of primes are in P, are in S rather, it doesn't matter. There's only two primes that can be placed next to P satisfying the condition. This is what we prove in the claim. And moreover, if there are multiple valid configurations, then removing P and stitching the two ends Q and R together, you will yield a valid configuration for S minus P. Because the rest, the neighboring condition is still satisfied. And we show that QR is also of the form x squared plus x plus k. So the stitch between Q and R also satisfies condition. You yield a valid configuration of S minus P. So if there are valid multiple configuration for the rest of the circle, you will end up contradicting the lower induction case. So proving the claim is sufficient to conclude the problem. So I think this is quite natural. You would, if you want to do induction, you'll probably hypothesize that you need to show this claim. Now, showing the claim is Slightly trickier, but once you have the claim, it's actually not too difficult. So let's prove the first statement. Suppose Q less than P can become neighbor of P. In other words, suppose Q less than P is such that PQ equals to A squared plus A plus K. Now for some integer A, but actually if A is less than 0, we can replace with minus 1 minus A. Because minus 1 minus A after you replace is the same numerical value as A squared plus A plus K. I just expand this out and check yourself. So without loss of generality, we can assume this is the case for some A greater than or equal to 0. And of course, because P squared is bigger than PQ, which is the expression here, which is bigger than A squared now, so A squared is less than P squared. So A is less than or equal to P minus 1. So putting these together, A is between 0 and P minus 1 inclusive. Now notice that if we take mod P, this thing basically says that A squared plus A plus K is congruent to 0 mod P. So A is the root of x squared plus x plus K in the finite field with P elements, which is really just a fancy way of saying that in modulo P, A satisfies the equation x squared plus x plus K congruent to 0 mod P. And there are at most 2 such solutions in FP because it's a degree 2 polynomial over a field. But of course, this is just a fancy way of saying that there are at most 2 such solutions mod P for this equation here, which you can either use the statement here or it's a statement from number theory. Now putting everything together, this means that there can be at most 2 primes that become neighbors of P. Take a moment to think about this. So obviously, same values of A will give same values of Q, right? Because you plug in here, Q is just this expression divided by P. So if you have 3 different values of Q that can become neighbors of P, then each of them must point to different values of A. So you have 3 different values of A, all of which lie between 0 and P minus 1, which will contradict the statement here that there are at most 2 solutions. So this is why there are only at most 2 primes that can become neighbors of P. So hopefully that is clear. We have proved the first statement. And the other part is really algebraic calculation. So we write PQ as A squared plus A plus K and PR as B squared plus B plus K. So suppose there's Q and R that works, and then we assume without loss of generality that A is bigger than B. So 0 less than equal B less than A less than equal P minus 1. So by subtracting one from the other, you get P times Q minus R is A minus B times A plus B plus 1. So this is not too difficult, but the key observation now is P divides this thing, but A minus B is strictly between 0 and P. So it must be the case that P divides this part, A plus B plus 1. And of course, A plus B plus 1 is at least 1 and is strictly less than P because of this inequality here. So the only possibility is A plus B plus 1 is equal to P. Now you plug this back into the equation here, the P's cancel, so Q minus R is equal to A minus B. And I'm just going to rearrange this by moving the terms to the other side. So B minus R is equal to A minus Q. And I'm going to call this common number D. It's just a notation. So if I use this D and I substitute A as Q plus D here and B as R plus D here, then this expression gives us P equals P equals A plus B plus 1, which is Q plus D plus R plus D plus 1. So it's this thing here. And the purpose of all of this is so that now I can look at my original PQ equals A squared plus A plus K, right? And I substitute in P is this thing we just last derived over here. And then A is Q plus D, which I plug in here, and A is Q plus D. So this expression, I now write everything in terms of Q and R and D. And you realize that QR is the term we are after, right? It's what we want to show to be of the special form. And indeed, many terms cancel out. Q square here cancels with the Q square here. 2dq cancels with the 2dq here. Q cancels with the Q here. So QR equals to D square plus D plus K. And so indeed, we have shown that QR is also of the desired form. Just a quick remark, notice that I had to prove the more general version of the problem because there's no guarantee that in my proof that D will be positive. So there's some subtleties in all the proofs I've seen on the AOPS forum that where the induction step requires prior knowledge about whether the D is any integer or is at least 0. So there is no single proof that directly proves it using the original question of positive integer. Yeah, so quite an interesting story there. There's some discussion on the AOPS forum about the problem committee realizing this at the last minute and they couldn't reprint the papers and so on. So quite fun, quite a funny story. So let's take a look at the statistics. The one interesting thing this year is that problem 2 seems to have a very high solve rate this year. So problem 1 looks pretty like normal. P2 is actually a lot higher than other years. I'm not sure if you recall last year's P2 was a monstrously difficult insane problem, but even if you compare against the average P2, above 50% of the contestants got full score on P2. And of course, P3 is the usual difficult P3, around 4.8% with full stop. So, thank you for watching, and next week I'll be covering the day 2 problems. So stay tuned and see you soon.